Good afternoon, everybody. This is the presentation on selection criteria for construction methods of multi-story underground buildings. This is actually a conference paper that I have co-authored with a group of previous students within the course Sanj 44, and it was in the CSCE 2015 conference. It was also co-authored with uh, the TA Muhammad Afifi, who presented that at that conference. First, what are multi-story underground buildings? They are several floors that are underground and could be used as car parks, basements, train tubes, shelters. Um, this is mainly due to space limitations above the ground, or maybe to because there is a necessity for it to be underground, like in case of shelters. So we will discuss three aspects here. First are the construction methods. Second is the site support systems. Third are the water level control. So first we have three major families of construction methods. First is the open cut. Second is the bottom up. Third is the top down. The major difference between the open cut and the bottom up and the top down is the sequence. So in the open cut, first you excavate. Then you construct all of the structure, the foundation and the retaining walls and the top. However, for the bottom up and the top down, you construct the walls first. The retaining walls are constructed first, and we will discuss the different types of wall systems that could be used. However, the difference between the bottom up and the top down is that in the bottom up, after constructing the wall, you excavate and then you construct the raft and you move up. However, and then you construct each floor. However, for the top down, you construct the uppermost level first, then you leave a room for yourself in order to get your equipment down, and then pour the lower level, then repeat it again for the lower until you reach the lowermost level, which is the foundation level. From this story that I am talking about, you will understand that the top down it will not need side supports because the slab is already acting as a side support and it is the fastest of all of them. However, you are working in a little bit congested area. So this is why for the bottom up system in specific, you will need side support systems. This could be done either using what we call cross lot bracing or the inclined bracing systems. This is if it is a temporary system. However, we have also a permanent system that could be a tieback or tiebacks or saw nails. And as you could see, all of these alternatives are expensive alternatives, and they add more in terms of the installation time to them. So you are adding more time and more cost to your project. This is a very simple comparison between the three different methods. And typically, as we mentioned, that the shortest project duration is the top down. The simplest to construct is the open cut. However, you have an issue with land ownership because you need to maintain an angle of repose. So you need to bear in mind a distance from any neighboring structure. So this is what makes the most common to be used is in the middle of a city, for example, is the bottom-up technique because it doesn't need that a lot of experience like the top-down, and it is again it is maintaining the safety of the neighboring structures. However, you need side support. You need some kind of a temporary bracing or a permanent bracing system in order to maintain the safety issue. So that takes us to the side support systems or the wall systems. So the wall systems are mainly classified into two big families. The, the site support systems are either watertight, like secant piles or diaphragm walls, or non-watertight, like sheet piles, soldier piles, and contiguous piles. Why do we classify it this way? Because if you are using a non-watertight technique and you are beside a high groundwater table, so you need to add some way of dewatering. You need to find a solution for a problem that will emerge. However, if you are using a watertight system, maybe and you are efficiently using it, maybe at a good depth, you will not need the watering from the first place. So non-watertight systems are, one of them is, the first one is sheet piles. Sheet piles is simply made of steel sections that could be temporary, could be permanent, but they have a maximum depth of 20 meters. The soldier piles, or the other name for it is Berlin walls, because they were actually used in the Berlin Wall. Simply, you have I-beams, and you have wall sections in between that could be wooden, could be concrete, could be steel. They are fast to drive, and in most of cases they are permanent, and they have a maximum attainable depth of 25 meters. Contiguous piles, they are simply concrete or slurry piles that are permanent for sure, and they are typically bored. Hence, it is slower than the other two. Uh, and the maximum depth, it will vary according to the cross section of the pile. So if you have a small diameter pile, it's different than having a large diameter pile. Secant piles are very similar to contiguous piles. However, because the piles themselves overlap by having what we call the plain concrete primary piles and the RC secondary piles that will overlap on them. Because of that, because of the thing itself, they are considered as a watertight system, and they could have a higher maximum depth when compared them to uh, uh, um, uh, contiguous paths. Diaphragm walls, they are the strongest of alternative of all, and they are the most watertight system. However, because they are larger and because they are more capital intensive, they are the most expensive. They could reach the deepest locations you could imagine. That photo, by the way, is from Cairo, from Tahrir Square, the garage during its construction. So mainly this is how you select between the different site support systems. The major factor here is whether it's watertight system or not, and the type of soil that we are talking about, because sheet piles and soldier piles are not suitable for hard rocks, and in some cases they are not even suitable for stiff clays. Contiguous piles, they are suitable for most of soils, however not for weak organic soils and not for hard rocks also. However, diaphragm walls, it is suitable in any soil actually. The speed, however, the issue of the speed, it's vice versa. The strongest is the slowest, and the weakest is the fastest. So this is another thing that would come into the picture together with the cost, because the lowest cost is the sheet piles and the highest cost is the diaphragm walls. These are the main factors that will govern your choice here. That takes us also to water level control. So maybe I will choose a non-watertight system because of due to time factors, due to cost factors. So I will choose a non-watertight system. So I will know that I will have water seeping into my site. So what should I do about it? So simply speaking, you could use one of two big families: either seepage cutoff, which is either grouting or soil freezing. So now you will play with the properties such of the soil itself such that it will not seep into. Or dewatering. I will dewater the site using well points or deep wells or electro osmosis or vertical sand drains, and all of them are called are dewatering different dewatering techniques. So our first case study here is the Tahrir Square underground car park, which is actually two car parks as shown here on that Google Earth map. You have two car parks with different capacities and different vehicle types. So before construction, they had to grout the area because they were working below, very, very near to the Nile. The top-down method was applied. They had a 27-meter deep diaphragm wall. The piles, which were actually then used as columns, were constructed. Then the slabs were constructed, and a space was left for the equipment to go down. Then the excavation took place towards the foundation level steps, while step 4 and 5 was going. Um, Again, when we are evaluating this method, a non-watertight would have needed a very large number of dewatering wells, so it was not an option from the beginning because it was near the Nile. So that leaves only diaphragm walls and secant piles to be used. And because the depth was large, so diaphragm walls were chosen because they were stiffer. And of course, open cut was impossible due to the groundwater table, and bottom up would have been extremely expensive due to the need of large bracing members. So that left top down technique to be the best alternative to be done. The second case study we have here is the Staines basement car park in UK. It's a two-story basement with an area of 3,650 meters square. The project duration was only 2 months. The depth was 8 meters, so it's something much smaller than the first case study. And the soil conditions were clay with groundwater at depth of 2 meters. So they simply used shade piles in such a case because the depth is small. At the depth of 14 meters all over the perimeter. Well points were used to suck water. The bottom-up technique was used in such a case because it's a small scale project and you not need a massive amount of temporary bracing here. And again, welding was performed. The raft foundation was constructed. Then the two slabs were constructed before dismantling the temporary bracing. Again, using a watertight system in such a case would be very expensive, which is something you don't need. So it's much simpler to use a non-watertight system and use dewatering in such a case. Excluding the open cut method was a correct decision because the groundwater table was high and it could cause side support failures. The top-down method is cost effective only in large scale project. However, in a small scale like that, it's not cost effective at all. Hence, the bottom up method was the most suitable alternative. In conclusion, the selection criteria that was presented has proven to be efficient in the two case studies, and it is highly recommended when you use this selection criteria matrix to be very aware that you should take everything into account because each project will differ than the other. This is the acknowledgements for the construction engineering department at AUC, and these are our references, and thank you for listening. Goodbye.